indexes, and we've seen that indexes allows us to speed up query execution. And we also were aware that indexing, when we create indexes, we have to be aware that there is a trade-off between the computational gain and the speed up of query processing that we gain versus the overhead that indexes introduce, both in terms of storage and in terms of maintaining those indexes when the underlying table undergoes inserts and updates and deletes. So we have to keep the indexes in sync with the actual underlying table, otherwise the index becomes useless. So we need to be very careful in selecting indexes in a way that the benefit is much greater than the associated cost. Now, we also seen many categories of indexes, but the main one we need to always keep in mind. We have the clustered index and non-clustered index. If you remember this discussion, what's the main difference between clustered and non-clustered?
The data itself is indexed, sorted. And
yes, the data, so in clustered index, the data is sorted in the order dictated by the index key. Also, the data and the index are one data structure. If we are, for example, using a B+Tree as a data structure for our index, the leaf of the tree will be the actual data blocks. So that is the idea of clustered index. Because of this, we can only have one clustered index per table. One clustered index per table. Now, the non-clustered index, yeah, if we use, for example, a B+Tree as a data structure, in the leaves of the tree, we will not find the actual data. We will find pointers to the data files. So the index is one structure separate from the data file in the case of a non-clustered index. Also, in a non-clustered index, the data is not necessarily sorted by the index key. The final distinction we also made that the clustered index are sparse indexes. So in each block, there is only one entry in the index. But the non-clustered index is a dense index. For each value of the index key, we will find an entry in the index. So we had this discussion last time, and then we kind of concluded by discussing that there are two major ways of creating, two major data structures for creating indexes, widely used data structures. There is the B+Tree, or more precisely the B+Tree in data structure, and we have the hash table data structure. Two major data structures are used. Of course, the indexing is a huge topic with a lot of research, ongoing research and development, and there are so many other data structures for doing indexing. But by far, those are the most commonly used one. And even the other ones that we might find, many of them extend those base indexing data structures. So in this session, I want to, this is the scope of this session. I want to really go through how this B+Tree index works and how we build one. How do we insert into this B+Tree, and how do we delete from it? And now we will do the same for the hash tables. So we will look into these data structures in very closely in the context of database management, and we see how they work. So that's what we want to achieve in this session. So first, I just quickly review the added value of using indexes. So without indexes, if we are looking for something, we will have to do full scan of that structure we are looking into. For example, in this, if we have an array of values or a file full of values, and we're looking for a particular value, we can do, if there is no index, we have to do full table scan or full data structure scan. luckily, if the data is sorted, we can do a little bit better than full scan. We can do binary search. If you recall the binary search, for example, if I'm looking for 27 in this index, I go to the middle value of this array. Let's just imagine that this is the middle value. And then I'll ask myself, the value I'm looking for, is it greater than the middle value or less than the middle value? If it is greater than the middle value, then I can simply ignore this part. Fully ignore this part and just focus my search on the second part. And in the second part, I do the same. I break it into two. And let's say this is the middle value. And then I pivot and say, I'm looking for 27, which is less than the middle value. So what I'm looking for must be in the first half. So I can ignore this half and focus on this second half. And then I keep breaking until I fall into the value that I'm looking for. I can do this, which is called the binary search. I can only do it when the values are sorted. If they are not sorted, the only way to find what I'm looking for is full scan. Yeah. Now, if I have an index, I can basically do an index access, and this will speed up the execution, or speed up locating what I am searching for. So as I explained last time, this is an example of a B+Tree. Yeah, let's say I'm looking for the value 35. I'm looking for the value 35. So what I can do here, I come to the root of the tree and ask, the root of the tree has this entry 17. I ask myself, the 35 that I'm looking for, is it greater than 17 or less than 17? Obviously, it is greater than 17. So you can see here, my search space is broken into half. This half I can safely ignore, totally ignore, and focus my search on the right side of the tree. Then I move to the next node in the tree and then ask, 37, is it less than 27? No, it is greater than 27, so I can ignore this. And now, basically, 35 is between 27 and 87. So I can follow this pointer here, and I will land immediately on the bucket or on the page that has the data I'm looking for. Yeah. So in three reads, I put my hand on the block that has the data. Yes, please.
Sorry for that, but
yeah, no problem.
The small table that with red, yes, the red table.
Yeah.
Has there is 17, but 2 empty. What that means?
Okay, this tree is basically being built. We will see how we will build the tree together. We will see shortly. So as the tree gets filled, it grows dynamically as you insert more data into it. So because the tree is empty, is still empty, there's lots of empty spaces. That's why these values there are no values in this. But as I insert more values, those positions will be filled, or those empty spots will be filled. But the concept is the same. When I come, so the idea of the tree, if I go this path, I find all the values less than 17. If I go this path, I find all the values greater than or equal. So this path is greater than equal, and this path is less than. And then when I land in the second bucket, second page, sorry, I keep using buckets. In the hashing, they use buckets as the terminology. In the B-tree, we use pages. Yeah, we don't use it's just terminology. Okay, now in here, so if I go this path, those are the values less than 27. This path is values between 27 and 87. And this path, values greater than or equal 87. Yeah. So through the example I just showed you, in 3 blocks, I get to the data that I need. And if you remember, when we discussed the buffer pool, the database will always give higher priority to this root of the B tree. And those roots will most likely remain in the buffer for a long time. So, which makes it effectively in 2 disk blocks in practice, you will get to the data that you want immediately. Yeah. So that is the power of indexing, the power of B-tree index.
Why we choose 87 here? It's not
We will come to how this tree is built. And here I just showed you how we can query the tree and how this query avoid full scan. This is I'm just trying to explain this one versus full table scan. Maybe the full table scan will be more appropriate if I have put these values not sorted. I will change this slide to put these values not sorted to show you that if they are not sorted, the only way to get to the values you're looking for is to do full scan. But if you use a B-tree, you reduce the time and effort to do it. You reduce the time of doing so. And more importantly, in the context of databases, you're reducing the number of pages that are read from disk, because that is the predominant component of the query cost. The less blocks we read, of course, the better. Okay. So in a single level indexes, which are theoretical indexes, in most databases, they don't use a single level index. It's always a tree. Yeah? So in a single level index, where I can find a key and pointer, you can think of it as an array of keys and pointers, and I can basically, it allows me to do binary search, as I explained before. So if you build an index that is a single level, it is still useful because it enables you to do binary search on that particular index, flat index in one level. But in practice, that is not how it is done. In most databases, they will use some kind of tree structure to organize the index. And that tree structure happens to be the B+Tree index. Okay, and that index will have multiple levels, and the tree is dynamic. As we will see the algorithm shortly, the tree will expand and shrink as you insert more data to it. The more data you insert, the tree will expand horizontally, and if needed, also vertically. In practice, most of the trees have 3 levels, most of the trees, as we will see. But it can be any level. And as you delete data, what happens to the tree? It will also narrow. It will be the depth of the tree will also reduce. So the tree, as you insert, it can grow horizontally, and it can also, if needed, grow vertically, and vice versa. When you are deleting elements from the tree, it will shrink horizontally and can also shrink vertically. Yeah. We will see this shortly, but this is just to visualize. I think you are now familiar with the concept that in an index, in practice, it's usually a multi-level index. All right, so the B+Tree is the most common data structure for indexes, and it can keep as many levels as required. It is a dynamic data structure. The number of leaves, the number of levels is driven by the data that you insert into it, as we will see shortly. Now, there is one rule when we build such B+trees. There is one rule, is that each block in the tree must be at least half full. Must be at least half full. And the B trees are very, very, very useful when we are talking about equality. It's very good for equality, but it is excellent for range search, as I explained before. So for example, in this simple example here, if I'm looking for values greater than or equal 35, all I need to do is to find the first record that meets my condition, which is in this case the first record where whatever it might be, let's say here the age. I find the first record where the age is, let's say 35, and then all I do, I land into the page that has the record I am looking for, and the remaining records to meet this query greater than or equal 34 will be just next to each other, like contiguous. The pages will be physically next to each other because these pages, in these pages, the data is sorted. Remember, the data in a B+Tree is sorted based on the search key, and these pages are linked. So each page is linked to the next page. So if I'm looking for entries where, let's say, age is greater than 35, all I do, I come here, get this block, and then read all the entries in this block that are greater than 35, and then keep reading the other blocks blindly, keep reading them and include them in the results without any extra filtering, without any extra effort in locating more records because the data is sorted. So the B+Tree is optimal for range queries and also for queries that require the data to be returned in order. Okay, so now let us dive a little bit deeper. So first, the B stands for balanced trees. Balanced trees means if we look at any leaf in the tree, such as this tree, any leaf in a leaf page, the distance between any leaf page and the root is constant, is the same, is equal. So, which is basically the depth of the tree is the same for all the leaves. That's one idea, one property that the tree preserves is that what is the distance between the leaf node and the root node? 3. So basically 1, 2, 3. So the depth of this tree is 3. Yeah. For any node, for any leaf node, this property is always satisfied. So that's why we call them balanced trees, because the depth at any leaf node is exactly the same. So from the root to the leaf, always we get the same length. As I explained, most of the B trees have 3-level indexes, and I will show you shortly that 3-level indexes can hold millions of records. In most cases is enough in practice, but the tree can grow to any number of levels. So they are similar to binary trees. Those of you who've seen binary trees in maybe some data structure course, but in here, the leaves, it's not just 2 leaf nodes. We can have as many leaf nodes as needed, as we will see shortly. So in the case of using the B tree in the context of a database, each node in the tree, the size of the node is exactly the same as the size of the page. Remember the page? That our data file or index file is broken into pages, and those pages have fixed size. So that fixed size is based on the database. Each database chooses a fixed size block or fixed size page. I think for a SQL Server, I think it's 16 kilobytes. So every node in this tree, if it is a SQL Server node, if it is a SQL Server B tree, this node will be able to store 16 kilobytes of data. Okay, so in a B tree node, what we find is 2 things. We find search keys. In a B tree, we have 2 things. We store 2 things. We store the search keys and we store pointers, n+1 pointers. So especially the the root node and the intermediate nodes. So first of all, let's distinguish between the various types of nodes we have. This one is definitely the root node. This one is intermediate node. And this one is the leaf node. Okay, so in every node, especially the root and the leaf, what we find keys plus pointers. Keys plus pointers, yes? That's what we find. So usually in a particular node, what we have is we have n search key and n plus 1 pointer. Yeah, n search key and n plus 1 pointer. Why n plus 1 pointer? Why not n pointer?
The first one or the last one. So between them and the last one.
So first, for the leaf node, if you notice here in the leaf nodes, for example, for the leaf nodes, they are connected, yeah. And for the intermediate node, every value basically has it's always n plus 1 because let's say in this example, the first pointer is pointing to values less than 27. The second pointer is for values between 27 and 87. And the third pointer is from greater than 87. So each node basically has n keys and n plus 1 pointer. Yeah, that's the basic idea. We will see this in more practical way as we progress through. But just imagine now the block size is 4 kilobytes. Imagine the block size is 4 kilobytes, which means basically what we can store in this block size, so we can have 4n, and imagine that we need 4 bytes for the key and 8 bytes for the pointer. So imagine the size of the key is 4 bytes and the size of the pointer is 8 bytes. So what we will have is 4 n's. So in a block of 4K, we can store 4n plus 8 times n plus 1 equals to 4096. Okay, so what this means is in a block of 4096 bytes, I can store 4n, which is 4 key values, and n plus 1 pointers. So the keys in this scenario needs 4 bytes, and the pointer needs 8 bytes. So how many keys I can store if I have a block of 4086, how many keys I can store? So I can work out, like, if I simplify this equation, n will come to 340. Yeah. So the leaf nodes, they can store up 340 nodes. Yes, 340 keys. So each node can store 440 keys, and they will have 340 keys, and they will have 341 pointers. Yeah. Now, if the page size is how many we said in the case of SQL Server? I think 16 kilobytes. Yeah. So 16 kilobytes. How many bytes? 1024. Yes.
The node has multiple keys, right?
The node will store multiple keys. Yes. So basically, if we have 16 kilobytes times 24, this is the total number of bytes. And in here, what do we have? It's 4n plus 8n, which is 12n.
Yeah, minus 1.
Minus 1.
Divided with 12.
Minus 8? Ah, yeah, of course, yes, thank you. Minus 8. Divided by 12, yes? 1364. So if the page size is 8, if the page size is 8 kilobytes, or sorry, 16 kilobytes, we can store how many keys? 1364 keys. And if we have 3 levels, then we can basically this number to the power of 3, which will be millions of keys that we can store in a particular tree level. In a tree that has 3 levels, we can store basically millions of records. That's why in most cases in practice, even there are some research studies, most of the B+Tree indexes are 3 levels. It can be more, but that's in practice. 3 is enough for even a large table. Okay, all right, so let us now get into a little bit more details and see how there are some small differences between the leaf node and the intermediate nodes. Small differences when it comes to that small differences and some slightly different rules that the tree need to preserve all the time. Some properties that the tree need to preserve. So the first thing is in the leaf node, the search key in the leaf node, the search key points to the data file. This one is which type of index where the search key points to data file? This is in the case of non-clustered index. Remember the non-clustered? Non-clustered index, the data is separate from the index. So in a leaf node, in a non-clustered index, we will find keys and pointers to data file pages. Yeah. In the case of a clustered index, what we will find in the leaf node? The data itself, the pages containing the data itself. Okay. So imagine now we have the leaf node that is for a non-clustered index. So the leaf node contains sorted lists of index entries. So that the leaf node, the entries in the leaf node are sorted. We need to keep this in mind. The leaf node entries are sorted based on the index key. The other thing is as we insert and let's say as we insert and delete entries from the index, the tree need to maintain in each leaf node at least each leaf node must have n+1 divided by 2, the floor of that value, which means rounding down that value. We should maintain always that minimum number of pointers. So for example, imagine n is 4, which means we can store in a leaf node 4 keys. So how many pointers we should at least have in each node? So 4 plus 1 divided by 2, which is 5 divided by 2, 2.5, and the floor is basically rounding down. So the floor of this one is 2. Yeah. So this is a rule. The leaf node must always have at least n+1 divided by 2 pointers. Otherwise, that leaf node will not exist. It should be merged. If we go below that value, that node needs to be merged with the sibling node. So the tree always maintains this rule. We will see when we go through the algorithm of inserting and deleting, we always verify this rule. The rule is very simple. If the node can store n keys, we need to make sure the node has at least half. Another way to say it, the node is at least half full. Otherwise, the node should be merged with other node. Okay. Now the other, and the leaf node in this case, can you see here the leaf node? Like we have keys and keys pointing to the actual data file. pointing to the actual data page. Node pointing to actual data page, node pointing to actual data page. And the last pointer is pointing to the next page in the index. Remember, the leaves are connected. So that's why the node stores n keys and n plus one pointer. So n keys pointing to the data pages, and the n plus one pointer is pointing to the next page in the index. Yeah. So that is the idea. So you can see here, just to show you visually, in the index, the leave node of the index, the pages are connected. Each page is pointing to the actual next page. And this enables us to do a range query. So because once we land on a particular page, if we are looking for greater than, we just follow the pointer and get the pages, the subsequent pages that are connected to the current page. The last one will be null, which means that's the end. There are no more pages in the leave nodes. Yeah. Okay. Now, for the inner nodes, the inner nodes, they work slightly differently than the leave nodes. You remember, the leave nodes, the keys are pointing to data pages for non-clustered index. For clustered index, the leave nodes have the actual data pages. Now, the inner nodes point to leave nodes. And the way they do that pointing is the first pointer points to values less than the key. And the second pointer, in this scenario, for example, the second pointer pointing to the values between consecutive keys. Between consecutive keys. Yeah. And then the last pointer here, of course, we are still between consecutive keys. The second pointer is pointing to values between consecutive keys. And the last pointer is pointing to values greater than or equal this particular value. So if you follow this pointer, you will land onto the pages that store keys greater than or equal, in this case, 29. So that's how we read the intermediate nodes. That's how we read the intermediate node. Each key in the intermediate node has two pointers. Imagine there is only one value in the inner node. If there is only one value, the first pointer is pointing to values less than that particular key, and the right pointer is pointing to values greater than or equal that particular index key. Yeah. If we have multiple values, so the first pointer is pointing to values less than the key, and the second pointer is pointing to the values between this key I and k, let's say I plus 1. So the values that are in between these two values. And the last key in that particular node will be pointing to a leave node where the key is greater than or equal the actual value that we see in the inner node. Yeah, that's how we read it. Is clear? So in general way, if we have a particular pointer in the inner node, so that pointer will be, the first pointer will be pointing to values less than k1, and the second, if we find the pointer in, not the last pointer, and not the first pointer, some pointer that is in between, it will be pointing to values that are less than k I minus 1, sorry, greater than or equal k minus 1, and less than ki. And finally, the last pointer will be pointing to values that are greater than or equal the last key value, which is, in this case, kc minus 1. Yeah. And it's easier to read it this way. Is clear how we interpret those pointers? Okay, here it is even more clear. So you see here, every value have 2 pointers. So if we go this path, we will find values less than 84. This pointer values values that are greater than or equal 84 and less than 91. And the last pointer is basically values where the key is greater than 91. That's how we read those nodes. Okay, for the leave node, I already explained, each value, each key is pointing to a particular page and particular record, except the last pointer is pointing to the next leave node, adjacent to it. Okay. So if we look at a particular leave node, the leaf node, this is the structure of a leaf node. So each leaf node, it maintains some small metadata. For example, it maintains the level, which level this node happens to be. For example, in this particular example, the level will be set to 3. This is in level 3 on the tree. There is the slot, the number of slots we have, which is basically the number of keys this particular node is storing. We have a previous pointer and next pointer, so we can go left or right to neighboring pointers. And then we have the actual keys and pointers to the actual data file, to the actual data data pages, to the actual data pages. Okay. I explained this already. In the case of a non-clustered index, it will be pointing to, these pointers will be pointers to record IDs. In the case of clustered index, the actual value will be the actual record. I think this should be now clear by now, okay? So there are some constraints that the tree will always try to maintain. This is a summary of those constraints. The first constraint is the root must have at least 2 pointers. The internal node or the inner nodes must have n+1 divided by 2, the ceiling of the half, basically half the number of key. The node is half full. It must have n+1 divided by 2 pointers. And the leave node, exactly n+1 divided by 2, but in here we take the floor, which basically rounding the value, the results, rounding it down. And in the case of the internal node, we round it up. Okay. Yes, please.
There is a previous pointer also?
There is in practice, yes. In practice, there is a previous pointer. So, yeah, sorry?
This will point
to the previous page. Yes, yes. That is useful if you, although in this Mickey Mouse examples we will go through, we will not worry about it. But in practice, it is both ways. Because, for example, in here, if I'm looking for values less than 34, I need to be able to go backward. So I need 2 pointers, one pointing to the neighboring buckets on the right side, and one pointer pointing to the neighboring bucket on the left side. I will use this pointer if I'm looking for values greater than the values is stored in the current page, and I will use the left pointer for getting to the pages storing keys less than the keys stored in the current node. Yeah, that's why we need both. For the demonstration, we will just maintain one. Yes, please.
On the clustered index,
yeah.
Every key will have like three pointers, right? On the leaf key.
On the leaf? No. On the leaf, there is only one. Every key has 1 pointer.
So the pointer to the one before and one after, and pointer to the data.
No. One before and one after is maintained at the node level, not at the key level. You see here, this is a whole, imagine this is the leave node page. the page where there is only one, there are two pointers, one for previous, one for next. Not associated with the keys, associated with the whole node.
What about the last node and the leaf?
The last node in the leaf, of course, the previous pointer will be pointing to the previous page in the index, and the next will be pointing to null, which means that's the end. Yeah, that's basically indicating that that's the end of the pages of the leaf index, the leaf nodes of the index. The last page of the leaf nodes of the index will be pointing to null, meaning that's it. That there are no more leaf nodes. There are no more leaf nodes.
In real life implementation, like we will not worry about this at all. We just create clustered or non-clustered.
Yeah, of course. Yeah.
Can we control the level?
No, not really. No, we cannot control the level. No. How the level is controlled?
Can we have like 4 levels if I wanted my database?
No, that we don't control that. How is it controlled?
Minimizing the number of keys.
No, basically by. Yeah, we can control it. Thank you very much. We can control it indirectly by having a smaller key. If we have a smaller key, we will have a shorter. We can store more keys in each node, and of course we can have a shorter tree. Yeah, but basically the number of levels is decided based on the size of the actual index. The more keys you store in the index, the more you will grow. You try to grow horizontally as much as you can. Then once all the leaves, all the nodes are full, you have to split. We will see shortly how this works. And then sometimes when you split, you might split just the leaf nodes. Sometimes you need to split the inner nodes. And sometimes even the root node gets affected. Once you split the root node, then the tree will grow horizontally. Yes? Sorry, vertically. Vertically. Yes? So if you split only the leaf nodes or the intermediate node, the tree is growing horizontally. If this affects the root node and the root node needs to split, then you are growing also vertically. Let's just jump into the more interesting part, which is how the tree is used for querying, how the tree is maintained in terms of adding and deleting. The n is 3. N, which is the number of entries per node. In this case, for this simple example, we set it to 3. But in reality, as I mentioned, at least even if you have 4 kilobytes, each node will have 340. So if you go for a page size of 4 kilobytes, each node will have at least around 340 keys. But for demonstration here, we are just creating this tree. Each node can store up to 3 entries, 3 keys. Okay, so each node satisfies this condition. So we said that the inner node, what is the condition of the inner node? It should store at least n plus 1 divided by 2 pointers. N plus 1 is what? 3 plus 1 is 4 divided by 2 is 2. So every node has at least 2 pointers, which is fine. So for searching, I already explained this one, so let me just jump to it quickly. So if I want to search for value 22, what are the nodes that will be visited if I'm searching for value 22? How the tree will be used? So I visit the root node, and then? So definitely, because I'm looking for 22, which is I'll go to this key and follow this right path, because what I'm looking for is greater than this key value. Yeah, follow this path, and then I'll end up here. And I ask myself, 22, is it less than 27? Yes, follow this path. And this is the page, the index page that has the data that I need. Yeah. If it is clustered index, I arrive to my record. If I'm doing select star from students where student's ID is 22, I get all the data. That's it. If this is a non-clustered index, then this will give me the page ID and the record ID to get the actual data. Then I have to do one extra read. So what is the cost of this query? If it is, suppose it is a non-clustered index.
No?
4. So we will read this one. This is the first block we will read. We will read this block. Second block we will read. We will read this block. Third, and the data block, which is 4. So 4 blocks to arrive and answer this query. Yeah. Still much better than doing full scan. And in most cases, as I explained before, in most cases, the roots, most likely in 98% of cases, will be already in the buffer. So we will not count it. It will be, typically the cost will be the depth of the tree minus depth of the tree. Because the extra read that we will go to the data file, we saved it already by not going to the disk for the root node. So most likely, in the depth of the tree, we will get to the data that we want, and that's it. If I'm looking for all values greater than or equal 23, how many reads we will have? So the depth of 3 of the tree, which is 3, plus, basically, I will be reading this, reading the keys in the subsequent blocks, and for each key, I have to do a read, okay, from the actual page. So it will be the number of keys times the number of keys, basically. So it will be the depth of the tree plus the number of keys. This is in case of non-clustered index. In case of clustered index, it will be the depth of the tree minus 1, because most likely the first block is already in memory. And in case I want to read all, it will be plus 2 blocks. So in basically 4 reads, I'll be able to answer the query. You get the idea how the index is used? So for the clustered index, the data will be stored in the leave node. Yes? So if I'm looking for records where an ID, for example, is greater than 23, so I will do 1, 2, 3 to arrive here. So these are 3 blocks. Plus, this will give me the data that I'm looking for. Let's say I'm looking for values greater than or equal 23. Then I'll move to the next subsequent block. That's the 4th block that I read. Then I move to the 5th block, and that's it. I answer the whole query. I answer the whole query in 5 blocks. Yeah. And if I'm lucky, as I said, one of them, at least the root, will be already in the buffer, and it will be reduced by 1. This will be 4 blocks. Is clear? Okay, another example here. If I want to, which nodes I'll go through if I'm looking for value 16? Any idea? Value 16. So I'll come here, and so it will be to the left. I'll go to the left, and then 16 is greater than 10. I'll go right, and I will land here. Yeah, and I look up in this. I look up in this node, and 16 is not there, and basically I will say not found. It's not found on this page. So remember the architecture of the page of the node, or the layout of the node. The layout of the node, I have the keys sorted. So once I arrive to the node, super easy. I get it into memory, and I can very quickly scan those, do maybe a binary search or do some smart search in memory to find the key I'm looking for. If I don't find it, means what I'm looking for does not exist. That's basically how the search works through the B+Tree index. Now let's try to start looking into how the inserts work and how the delete works. Okay. Range queries, I already explained them. Range queries, whether greater than or equal, or whether less than, or whether a key is between two values, very easy to answer. Because the leave nodes are sorted and connected by pointers. So once I arrive to the initial node, I can quickly answer the rest of the query. Okay, this is the algorithm of inserting. I will come back to it after I show through an example. Then we go through kind of the general description of the algorithm. Okay. So here it is. So I want to insert, let's say I start a new table, fresh table. Never, like, this is a new table. I have never inserted anything into it. And I create an index on that table. So initially, the index will be flat index with one node. And the node here, as we discussed, will have 3 entries, where n is equal to 3. So in this particular example, n, interesting, how do I write? Okay, sorry, here it is. Okay, so n equal to 3. So somebody inserted some rows, and the primary key or the key happens to be 2, 21, and 11. Yeah, and suppose this is unclustered index. So what I will have my node that will have three values. So I will insert 2. In the beginning, I will insert something like this, 2, and the 2 will have a pointer to the data file, and there is no next pointer. The next pointer will be pointing to null. There is no next pointer. Then 21 comes along. I put 21 here, and it will be pointing to the data file. And then the next, there is no next, so the next will be null. And then I'll have 11. So 11, I'll have to kick this one to the left, because remember, the keys must be kept sorted. So this will be 11, 21. Yeah. So at the end of the day, this is what I will have. I will have my first node full. Now, any new inserts will cause some splitting. The tree will start forming and will start growing. So whenever you have a data structure, of course, you have to also have an associated algorithms to insert and update and query. The algorithm for querying, we already seen it. We are now trying to discuss the algorithm for inserting. For the first part is easy. Now, second part, here is my initial node after I inserted 3 values, and now the leave node, or this first node, is full. When I come here, I want to insert 8. Yeah. So what will happen when I want to insert 8? So the capacity of the node is n equal 3. It cannot take any more values. So what I do, I have to split this node into 2 and form the tree. So what I'll do here, I basically create another node here. Yeah. And here is 8. So I'll take these values, get them sorted. 2, 8, 11, and 21. Yeah. I divide them into half. Half will go to one node, and the other half will go to the other node. So in this case, the first node will have 2, 8, and the second node will have 11, 11, and 21. Yes? And then, basically, I form here my root. Yes. Okay. All right. So I form here my roots, and the roots, what I'll do, I'll go to the new page that's created, and the first value of the new page gets copied into the root, and then I'll add my pointers. Okay, so this way, values less than 11, people looking for, let's say, value key 8, they will take this path. And people looking for, let's say, value 21, which is greater than or equal 11, they will take the other path. And this is the tree how it is formed. So to summarize, when a particular page becomes full, what I do is I split it into two. Half of the values will sorted. Half of the sorted values will go into the original page, and the second half will go into the new page. Then I take the value in the new page, the first value in the new page, and copy it in the new root node, and then create 2 pointers pointing to the pages. And this way, my tree has grown two ways. Has grown horizontally by adding one extra leaf node, and of course, to be able to connect these two leaf nodes, I have to have a root node, and then now the tree has also grown vertically. Yes. So that's the idea. So let's see if this is. Let me see if I can. Okay. Let me do it through the animation now. So I posted this not in PDF, I posted in PowerPoint, so you can go through the animation. So here is inserting 8. So what I will do here, create a new node with the last half of the values. But when you create the new node, make sure the values are sorted before you create the half. So the 8 in this case will be 2, 8, 11, 20, 21. Half will stay in the original page, and half will go into the new page. Okay, that is done. And then I have to chain these nodes. Of course, I have to chain them because remember, the pages are connected. So the original page will be now aware of the new page, and it's pointing to it. Then I go and create a root node. When I create the root node, what I do, I take the first value, of the new page, and I copy it to the root and create 2 pointers to the 2 pages that we have. Is clear? The insertion? Okay. Moving on, I'll insert some more. Here is my tree so far, and I want to insert 64, then 5. Now, if I want to insert 64, how I will do it?
Check if bigger or less or.
Yeah, so 64 is greater than 11. So which path I will take? This path. There is space there, no problem. I'll put my 64 there. Yeah. 5. 5 is less than 11, so I'll take the left path, and then I land in this bucket. Yes, and keep the keys sorted. So I'll push this here and insert my 6 in there. Yeah. Okay. 5, sorry. So both nodes are now full. So now the leaf nodes are full. Any new inserts will cause a split. And we will see how the tree will grow. So let's now try to insert 23. So inserting 23, what do you think will happen? So which path I will go? The right path. I land into the second page. Second page is full. What the algorithm says? Split this page into 2. Half of the values stay in the original page, and half goes into the new page. Yeah. So I will basically have a new page here, and what values I will have in here. So the value I want to insert is 23. So it will be 11, 21 will stay here, and 23 and 64 will come here. And then I'll go ahead and link these two pages by making pointer. If I have two-way pointer, I will have two pointers, previous and next, but for simplicity here, I'm just doing the next pointer. And then what I will do, take the first value of the new page and copy it to the root. So here, take this 23, put it in here. Sorry, 23, put it in here. And then basically, this is still hold. Sorry, this is 23. This still holds. So for values less than 11, we go this path. Values between 11, greater than or equal 11 and less than 23, we go this path. Values greater than or equal 23, we go this path. So we add one more pointer. And that's it. We are able now to grow horizontally. Yes? Okay. So let me just go through this one more time. Okay. So this is exactly what happened. It's just, I think this is exactly what we did. It's clear, yes? Okay. Now, the next step is we want to insert 6. So what will happen? So 6, which path we will take? We'll take this path because 6 is less than 11. And then we land in this bucket, in this page. This page is full. You guessed it. We need to split it. So we split it. So the way it will look, we'll have two pages. Okay. So, and this is another page here. So 6 will be between 5 and 8. So 2 of 5 will stay in the original page. And in the new page, we will have 6 and 8. We will connect these two. And then we will basically copy this value up to the root node. So the values in the root node will become 6, 11, and 23, and we adjust the pointers. So basically 23, this pointer will be moving here. This pointer will stay there, and we have, no, sorry, we will have a new one. So basically this pointer will be pointing here. This pointer will be pointing, no, sorry, this pointer will have two pointers. This one. What I'm doing. This one is here. This one will be going here. This one will be going here. And that one will stay in this one. Yeah. So basically we adjust the pointers and we make sure the pages in the leaf are connected, pointing to each other. Okay. So this is what's happening. Then we adjust the pointers. We copy 6 over to the root, and we adjust the pointers of the root. And that's it. Our tree is now fully updated. Okay? 6 is inserted successfully. Let's move on. Let's now try to insert 19 and 9. So 19, if I want to insert 19, 19 is between 11 and 23. So I follow this path. And basically all I do, I insert 19 here. There is space. Yes, so here 11, 19, 21. Inserting 9. So 9 is between 6 and 11. So I will go to this bucket and just simply put 9 here. Very simple. Okay. So this is the tree after we did the insert. Now let's move on. Inserting 7. 7 is between 6 and 11. So we will come here, yes? And then this one is full. Yeah, we need to split it, okay? So how things will look like.
6, 7.
So 6, 7 will be here. And then 8, 9 will be here, okay? Now, here is 8. Of course, I go ahead and connect those, adjust the pointers and so on. So what happened here, what I need to do now, take this 8
And copy it to
and I'll copy it up. Copy it up. So the,
4.
yeah. So I'm trying to do here, copy up 8 to here. I cannot do this because this one is full. And what I will need to do now, split the root node. Once I split to the root node, what happened to the tree? It will grow vertically. You see here? So the tree keeps growing horizontally, but if the splitting arrives to the root, the tree has nothing but to grow vertically as well. Yeah. Okay. So how we will do this now? So what we will do here, we'll have 2 pages. Yes. So the values we will have 6 and 8. Yeah. And 11 and 23. Yeah. Okay. So these are the values, 6 and 8, 11 and 23. Yeah. Okay. Now what we do here, make the root node. Now, for the root node, what we do is from the leaf to the intermediate node, we copy up. Yeah. When we are forming the root node from inner nodes, when we forming the root node from the inner node, we don't copy up. We basically push up. So this 11 will be pushed up to the root. So basically in this node, we will have 23 only. And the 11 will be copied here. And then 11, this is 11. And then we create our pointers. So this is the only difference. So from inner nodes to root node, we don't copy up. We push up the value. First value in the new page. That's what the algorithm says.
There were pointers to 11 here. From the one that was root. So the pointer would go.
We basically adjust the pointers. So let me just undo this. And just go through this slowly. Okay. So I want to insert 7. So 7 is between 6 and 11. So I split the leaf node, and I have 2 pages. The page having 6 and 7, and the new page having 8 and 9. Of course, I go ahead and adjust the pointers. And then I'll try to take 8 and copy it up to the root node. Because I'm in the leaf nodes, the operation is copy up. I'll take 8 and try to copy it up, but the root node in this case is full. I have to split it. Once I split it, remember the tree must have always a root. So this case, I will go ahead and split, insert 8 in the parent. So I will have 6, 8, and 11 and 23. 6, 8, 11, and 23. Now what happened is, as I explained, So the second bucket or the second page will have the values 11 and 23. What I do with the first value of the new page, I move it up to the root. I move it up to the root. So here it is. So half of the pointers go to the old page and half will go to the new page. And then adjust all the pointers and copy the first value of the new node, move it up. Not copy it up, move it up to the root. And adjust the pointers. Yeah.
So if it was in the leaf, it will be 11, the new
Yes.
node, it will be 1123.
Yes. From leaf to root or intermediate is copy up. From intermediate or inner node to root node is move up, push up. Yep. We push up the first value of the new page and we adjust the pointers. Is clear? Okay, let us move on. So now let's insert some more values. Yes, please.
Can you go previous?
Yep.
So how the 23.2, so the one that is greater and one that is lower?
Yeah, you see every pointer, if you remember, the first pointer pointing to the left is the values less than the key. And pointer pointing to the right is values greater than or equal the key, which is still correct here. So here, values less than 23 is 11, 19, 21, and values greater than or equal 23 is 23, 67.
Right, Victor? Suppose now I want to search for 11.
Yes, if I want to search for 11.
On the root, and the data is on the leaf. So how I can manage to not take the root one and go to the leaf to take the data? How can I know that the leaf has cluster?
Okay. So first of all, remember that the root node and the inner nodes, they never store any data and they never store any pointers to the actual data. They are just there to help us with the search, reduce the search space. So in the root node or the intermediate node, I might not find the exact value. I have to go all the way to the leaf to confirm whether the value is there or not there. So I'm not sure if I'm answering your question, but basically if I'm looking for value 11, exactly 11, the algorithm of search says the right pointer pointing to values greater than or equal the key, which is in this case 11. So I'm looking for 11. Which path should I take? The right path. Take the right path. I land into the intermediate node. The intermediate node, I find a key there called 23, and I'm looking for 11. So 11 is less than 23. This node is just navigating, helping me to navigate. It says, okay, go left. I go left, and I land on this page. This page, I bring it to the buffer, and I scan it in memory. Now it's in memory. I scan it because I have the keys. They are sorted. Now I can use those of you who did your courses here, we have a course called 303, Data Structures. There you study all the types of algorithms for search. One of them could be binary search. Now you are in memory. Everything now in memory. You just do it. Even if it is the worst algorithm, it is still fine because that is not the primary factor affecting the performance in case of database. The primary factor is reading from the disk.
So for every search, I need to go until reaching leaf.
Yes. Until you reach the leaf, you cannot make final decision. You have to reach the leaf. And the whole tree, the tree does not have, the upper tree does not have an entry for every key. No. Only for some of the keys. In fact, only typically the first values of the key. Sort of. the leaf nodes, they don't have all the keys, so you cannot rely on them to make a final decision whether what you're looking for is there or not there. You have to make it all the way to the leaf node, and the leaf node in there you make the final decision. You need to bring the whole leaf page to the memory, because remember, at the end of the day, you cannot read one record. You have to read the whole page. Then you scan through the keys and make the decision whether it's there or not found.
Doctor, maybe because we deleted them in first 11 when we inserted them. Maybe we should go to the leaf and we didn't take the division from the intermediate node to determine that 23, it was inserted, but and I don't know if it was then deleted or not. So because of this, I should go to the leaf.
No, like the roots and the inner nodes only store partial, like subset of the keys. They don't have all the keys. So you cannot make a decision. Oh, I didn't find the key in the leaf node, in the root or intermediate means that particular record does not exist. You cannot make that conclusion. You have to arrive all the way to the leaf, scan the keys in the leaf, then make that decision whether you find what you're looking for or not, or didn't find what you're looking for. Does that answer your question? So basically, the roots and the inner nodes are there just to help to speed up getting to the leaf, but they don't liberate you from shortcutting and making a decision before you reach the leaf. They are just there to navigate, to help you navigate in super fast way to the correct leaf node. Is clear? So you need to go to the leaf to make the final decision and to get the data, if it is clustered, or to do yet another read to the data page for the values that you're looking for. Okay, inserting all these values, 31, 39, and so on. Let's see what happened. Insert 77. Let's see what 77, how we will insert 77. So 77 is greater than 11. Yes. So we code this path. And then 77 is greater than 60. So we go this path and we land in this page. This page is now full. So what we have to do, split the half stay in the original page, half go to the new page. The first value of the new page, we copy it up to the intermediate node. If there is space, we are done. We just adjust the pointer. If we are not, if the intermediate node is full, we split it, and then we take the first value of the new intermediate node and push it up to the root and adjust the pointers. So that's basically the algorithm. Okay. So in here, as you can see here, we split this. So 60 and 64 will stay here. 77 and 93 will 77 and 93 will go into the new bucket, the new page, and then we take 77 and we copy it up. We copy it up to this node, and what happened to this node? It is full. We split it. So what we will have? 23, 45, and 60 and 77. So what we do to the 60, which is the first value of the second page, we push it up, and then what we will end up with 11 and 60. Yeah, and we adjust the pointers. Okay. Okay, so 77. So we push 60 up, and then we adjust the pointers. Yep. Okay. So now back to the through the example, it's easier, of course, to understand the algorithm. You can, of course, express it mathematically and confuse everybody, except if you have very strong abstraction. You can read very abstract formulation. But you can go through an example and then go back to not so mathematical, but kind of plain English algorithm. So to do an insert in a B+ tree, what you do, the first thing is you find the correct leaf node. Put the data there in a keep in sorted order. If the leaf node have enough space, خلاص, you are done. If the leaf node does not have enough space, you need to split it and distribute the values evenly between the two nodes. Then what you do is in the new page that has been created, you take the first value of that page, copy it up to the inner node. If the inner node has space, just you need to adjust the pointer and you are done. If the inner node is full, you have to split it also. And then when you split it, you take the first value of the new inner node that was created and you push it up to the root. Yeah? You keep doing that. Once the root is also full and you try to push up something to it, then you have no choice but to do what? Split the root. Once you split the root, the tree will grow vertically. Yeah? And you create another root and you push. Whenever you are not dealing with the leaf, you always push the value up. Not copy it, you push it up. That's basically the idea. So this can happen recursively, splitting an inner node, redistribute the entries, but push up the middle key. The middle key is basically the first value of the newly created page. Splitting grows the tree horizontally, but if the splitting reaches the root, then the tree will also increase vertically by increasing the height of the tree. So that's what I mean by this data structure is really dynamic. It's data driven. The more you insert, the more levels will be created. Okay, should we stop here for 10 minutes?
Sorry, but so
Yeah.
as a summary, for example,
Yeah.
after splitting,
Yeah.
the first key will be pushed up, which then you...
No, depending on what are you splitting. If you are splitting the leaf,
I mean here, for example, no, the middle.
at the middle you push up.
Push up
Yes.
because the new, when we split, it should be, for example, 60, 77. No, the first one is 77, then we push 50.
Yes, we push it up to the
Because
root.
the 77 becomes instead of 60.
Yeah, because we pushed up, the 77 will be the first value in the page. Yeah. Okay.
So always after splitting, it will be empty node at the end of the first.
No empty node. There is no empty node is not allowed, of course.
So I mean, because 60 pushed up, it should be empty.
No. 60. Remember here, if we didn't push up, we would have been here, we would have 60 and 77. So instead, we pushed 60 up, so the new page only has one entry, which is 77.
The last one, it should be empty. Yeah, yes, it's
Here?
the middle. The last one will be empty also?
No, not empty because of this, because we have 4 values, we split them. 2 stays in the original page, and the 2 goes into the new page.
I get it.
You get what I mean, yeah? And then the first value of the newly created page, we push it up to the root. Okay. So inshallah, when we come back, we will look into the deletion algorithm. Yes.
بس احنا التايم تبعنا هيكون على طول بعد المحاضرة.
Yes.
مش عايزين المرة اللي فاتت كنا نقوم قبلنا فتأخرنا.
لا inshallah, I always assume this one. What I will be discussing is the delete algorithm. Let's try to see if we can make sense of it in a generic way, and then we go ahead and see it practically through some demonstration. So deleting, I start always from the root, look up the leaf node where the entry belongs, and then remove the entry. Go to the leaf node, remove the entry, and then check the condition. Remember, there is a rule that a leaf node must have at least n+1 divided by to the floor of that value pointers. That's the minimum. If that minimum is not met, then it's time to merge. No, before we merge, we try to redistribute. We try to distribute by borrowing from the sibling. So if we have sibling node that has the same parent, it must have the same parent. The sibling node with same parent, we can borrow from it. So we can make things balanced, and we can meet our quota, which is the minimum is n plus 1 divided by 2, half full page. We cannot tolerate less than half full. And if we cannot borrow from the sibling, because the sibling also will not be able to meet its half full condition, then there is no other way to just, we have to merge. We have to merge that particular page with the sibling page, merge it into one, and then this merging might cause merging of the intermediate node, and that merging can propagate to the root and can collapse the height of the tree, can reduce the height of the tree. So similar that the tree was able to grow horizontally and vertically, the same thing. As we delete entries from the B tree, the tree shrinks horizontally, and it can also shrink vertically. Okay, so that's the idea. Let us try to see it now in practice, how it looks like, by going through some examples of deleting from the trees that we have built earlier before the break. It is the tree so far, how it looks like. So we want to delete 19. So we go here, this is 19. So 19 is basically between 11 and 60. So we follow this path. 19 is less than 23. We follow this. We go to this page. This is the page. And then we'll take that page. We bring it to memory and basically delete 19. Okay, we will end up with 11 and 21. So far, we will have already 3 pointers. 2 pointers to the data and 1 pointer to the next page. And the rule says we have to have at least n plus 1 divided by 2. So here n is 3, plus 1 is 4, divided by 2 is 2. So the page has more than 2 pointers. We are fine. So 19 wants peacefully, no problem. Delete the record in the data file. So if it is pointing to the data file, of course, we have to delete the record in the data file as well. Okay, delete it. We check the condition. The condition is still satisfied. We move on. Now we delete 45. Here is 45. So we go through our tree. So 45 is between 11 and 60. So we go through this path. And then we'll say 45 is greater than or equal 45. We go this path. And then we'll end here. And we remove 45 from there. So in here, we remove this 45, and then we end up with 51. So we'll end up with 1 pointer only. This page only have 1 pointer, which is less than half full, violating the minimum occupancy. So it need to borrow from the neighbor or merge with the sibling. Either borrow from the sibling or merge with them. Okay, so luckily here, we can borrow from the sibling. So we'll borrow from the sibling. We basically, 45 will come here, 39 will come here, and we copy it up to replace 45. So that will be 39 there. So let's see how it looks here. So 45, we go ahead, search for the value first, delete the record from the file, and then we'll check. So the node is less than half full, but luckily with the neighboring parent, with the sibling having the same parent. You cannot be a sibling that does not have a same parent. So we can borrow from the sibling, left sibling, so it will be 30. The new content will be this bucket this page will have 3951, and then we will basically copy it up to replace the value that was there. So 45 that was there is replaced with 39. Okay, and that's it. Finish this one. Change the value of the parent node. Okay. Now let's go and try to delete 9. So you know the path, we'll go through the path, and at the end of the day, we will land here. And we'll go ahead and delete 9 and delete it from the data file. And then we'll end up with 8 only. 8 has one pointer to the data file. It's less than half full. It's violating the occupancy policy. It needs to borrow from the sibling having the same parent. The sibling, if it borrows from it, it will suffer from the same problem. So we cannot borrow from the sibling. What we have to do? Merge with the sibling. Okay, so let's see how it looks like. So once we delete the 9, we have only one pointer, and the sibling we cannot borrow from, so we merge. So by merging, basically this bucket, this page here will be removed. Yeah, because this page will be removed, also the pointer will be removed, and this will be removed. Sorry? There is no need for, no, 9 is gone. So because we removed this pointer, we also remove this value, and basically we have here 6. And 6 has 2 pointers, so it already satisfies the condition. There's no problem. So let's see. So we remove the buckets, we remove the page, we remove the pointer, and we remove the entry associated with that point. Yeah, and this is how the inner node looks like now. So moving on, this is how 9 is done. So basically we delete it from the leaf. We try to borrow from the sibling. We cannot borrow. We merge with the sibling. And then we delete the pointer. We delete the value associated with the pointer in the inner node. And that's how it looks like after the delete.
Excuse me, what is the condition?
The condition is the pointer, the inner nodes must have n plus 1 divided by 2 pointers. N in this case is 3, plus 1 is 2. Sorry, plus 1 is 4, divided by 2 is 2 pointers. So this page still have 2 pointers, or this node still have 2 pointers, so we are fine. Okay, all right, moving on. So what we want to do is we delete 6. Yeah, we delete 6. How we will go ahead and delete 6? So 6 is less than 11, we end up in there. 6 is greater than or equal 6, we land in this bucket here. Yeah. So we delete 6, and this page will be 7 and 8, and we copy this 7 up here to replace 6. Oh, interesting. It's gone? Oh, sorry. Yeah, 6 is fine. What did we delete? Deleted 6. Yeah, so this is how it looks like. Deleting 8. Now we want to delete 8. So deleting 8, we will land here. And this will cause what? So once we delete 8, we cannot borrow from the sibling of the same parent, remember. And then we have to merge. So we merge these two. Once we merge, this will be deleted. And now we have a problem, because this one has less than 2 pointers. So this cannot exist on its own. So we need to borrow from the sibling. Yeah. But it's interesting how we borrow. We need to borrow what? 23 from the sibling, yes? How we will borrow it? We just copy it here, or how do we borrow it? We basically make it do a big bounce. We push it up. This 11 will fall here. Yeah, that's how we do it. So we push this up, 23 will come here, and 11 will land there. That's how we borrow. So when we borrow from the sibling in the inner node, we borrow it by pushing it up to the root, and the value to be replaced in the root is the one that gets borrowed. Is clear? So let's see it visually. So once we delete 7, everything is merged. And then once we basically merge these two buckets, this inner node now cannot exist like this because it has less than 2 pointers. We have now to borrow from the sibling. So borrowing from the sibling, okay, so that's how we borrow. So we will take 23, push it up, it will replace 11, and 11 will come down to the inner node. Yeah, that's basically the idea. And then we adjust the pointers. So the only idea to keep in mind here, in the inner node, when we want to borrow from the sibling, it has to go through the root node. We push the value we want to borrow up to the root, and the value it's replacing in the root will come down to the inner node. That's how it is done. Okay, you might be wondering what is this. This basically might be some PhD work or some research paper work or some. So it's a very nice algorithm that has been developed. Somebody suggested it, people liked it, and people start improving it until it became so widely used. Most databases use this data structure and associated algorithms to maintain the B+Tree index. Okay, that's it for the delete. That's the idea of delete. So handling, all I have shown you so far, I showed you the example where the keys are unique. The keys are not repeated. Yeah. Now, if the keys are repeated, we have two solutions. Either we repeat the keys. Can you see here the keys are repeated? Key K1, K2, K1, K1, K1 is repeated. Let's say this is the age, or this is the number of courses the students already took. That could be the key. Many students might have the same number of courses. So the key will be repeated. Either we will repeat the key repeat the key with the pointers. That's one way of doing it. Another way of doing it is we put the key only once, and the associated pointers are basically an array or a linked list. This is just some kind of implementation details. These are the two ways of organizing your leaf node when you have duplicate keys. Either get the keys to be duplicated in the sorted key array, or only maintain one key, but the value, instead of being one pointer, it will be an array of pointers or a linked list of pointers. So this is how it is done. Now, this is just to illustrate that a tree with the height of 3 levels, the height of the tree is 3, and the page size is 4096, which is 4 kilobytes. This tree, basically, as we discussed before, it can store up to 340 keys per node. And because we have 2 levels, and let's suppose it's only 2/3 full, so let's say we can only store, we will be storing in average 255 pointers. So in a 3-level tree, in a tree that has 3 levels, we can store up to 255 to the power of 3, which gives a couple of millions, 16,600,000 records. This is assuming a page of 4 kilobytes and only 2/3 full. We can store these values. Imagine we have 16 kilobytes we can store even much more. That's why most of the tables usually have 3 levels. We can have more, but just this is to illustrate that 3 levels in many cases is enough. Plus, in commercial databases, they do what is known as compacting the key. So they make the key shorter by compressing the key. This way they can store more keys per node, and we can have shorter tree. Because shorter tree means less blocks we need to read when we are doing the queries. Okay, so one way to improve the efficiency is to always try your best, of course, to pick up a short key. And if not, the database will try to shorten the key behind the scene by some smart compression algorithms. Okay, this is what I just mentioned. Okay, that's it for this one. I want to now jump to the second data structure, which is the hash table. Okay, so I don't need to save. I put it in a separate slides just not to have not to be very big set of slides. Okay, so this is the hashing. Hashing is another very popular data structure for managing indexes. Now, hashing, most likely you have seen it before in some kind of algorithm course. If we take a small example of a hash table, let me try to do it. Let me try to do it here. Yeah. So let's say I have here for an array of size 4. Basically, this is the index of the array, 0, 1, 2, and 3. Yeah. So this is an array of size 4. And then I want some super fast way of storing and retrieving values from this array. So let's suppose I want to store these keys, 5, 4, and 7, and 10. So one way to do this is to use a hashing algorithm such as, yes, so what I will do, I will take the key, apply some hash function, and by applying this hash function, it will give me the index where I should store or where I should retrieve this particular value, this particular key. So, for example, in here, one of the famous and very simple, super simple hashing function is to use the modulus, the size of the array. In this case, the size is 4. We use modulus 4. So what we do here is we take the value 5. 5 modulus 4 is what? 1. So 5 divided by 4 is 1, and the remainder is 1. So that's the modulus, basically. And then we basically put 5 here. Now, 4 modulus 4? 0. So 4 goes into here. So what is our hashing function in this case? Is basically the key modulus 4, modulus n. Key modulus n. Okay, now if we want to store 7 modulus 4, 3, and 7 will be stored there. And 10 modulus 4, 2, and 10 will be stored there. Now, if this is an index for a table on a file, these basically will be associated with a pointer. This will be associated with pointer pointing to the page ID where this record will be found. But the same idea is that when I want to store or retrieve some keys, I take the key, apply some hash function to it, and I'll get the index. And that index in the context of database will be pointing to a page on the disk where I can go and get fetch the actual data that I'm looking for. So if I, for example, if I'm looking for the value 7, how do I find this value 7 in my array? By applying the hash function. 7 modulus 4 is 3, and I immediately go into that element in the page. So in terms of complexity, the complexity here is 0.1. The speed or the computation needed to locate a particular element in my data structure is constant. Because all I need to do is take my key that I'm looking for, apply the hash, and I'll get the address where to go and retrieve the value I'm looking for. In the context of database, these values that will be stored here will be associated with the pointer, pointing to the page. Let's say these are students' IDs. This student's ID 4, I will have the page ID where I can find the record of the students with ID 4. And I can go to the actual page on disk and retrieve it and get the details. Yeah? Is kind of clear here? Now the challenge is to find like a good hashing function that will be first of all very fast, because we need to be, this hash function supposed to be super fast. And the other thing about this hash function, it should not create collisions. What do we mean by collisions in this context? Multiple keys resolving to the same position. Yeah. So in a real scenario, if we end up with collisions where multiple keys are land in the same position, what's the solution? What's one of the solutions we can do? Change the hash function. That's another thing. We will change the hash function. Maybe not, because usually the system in real life will choose some hash function. I'll show you some practical ones shortly, and we'll use it to do this hashing.
Increase the number, for example, n it would be more.
You can expand the storage capacity of your array in this case. Yeah, you can increase the storage capacity or change not the function, but change the parameters of the hashing function. For example, here we have modulus 4. I can double the size of the array and become, let's say I make it 8, and then the hash function becomes modulus 8. And this way I can reduce the collisions. But I might still end up with some collisions. In some cases, I can just solve them by having a linked list. And this is, we call it overflow. In case of database, we call it overflow buckets. So usually in a hash index, in the context of a database, it's always we have a hash key associated with a value. And these values are nothing but pointers to the actual data files, the address of the page ID, the page ID basically. It could be page ID and record ID, page ID and record ID. Remember, in here, these entries could be actual pages in disk. I can have a key, can have multiple associated values. For example, let's say the key is age. Let's say people who with 30 years of age, I might have multiple entries for them. Yeah. So if I fill up the available slots in my value, I can overflow by having chained pages. But this will affect performance, because not only I can just, in the normal case, ideally, I should just get the key, apply the hash function, land into the correct bucket, and I'll find my pointer there and go and get the data from the page. But in here, I have to visit other chained buckets to look up where the data is located.
So, Doctor,
yes, please.
Here, for example, I have 3 locations, right? 7, 10, 13.
Yes, 7, 10, 13. all of them have this
Yeah, the same. So,
key.
so for example, if I want the data of 10, I have to visit 7 and 10.
No, sorry, this is hashed key, sorry, not the actual key, this is the hashed key. So in here, what I mean here, in the, let's say somebody is looking for value 10, for example, some value 10. I apply the hash function, I land in here. So in here is luckily the value is 10 here. This value 10 will have an associated pointer pointing to the actual data file, and I'll go and fetch the record from the data from the page, from a particular page. But if I don't find, let's say I'm looking for 22, I take 22, apply the hash, and I will land in this bucket here. But in the values associated with this bucket, I cannot find 22. I have to keep looking in the overflow buckets. Yeah. In the context of database, this could be pages on disk storing these keys. And this will affect my performance. So it's no longer a constant O1 complexity. It's constant just to arrive here. And then I'll have to do, to follow the chain of overflow to actually get to the data page where my records, the record I'm looking for. So this happens when I have a hash function that creates collisions. Create collisions means all these values, they have the same hashed key. Yeah. So I'll end up with these collisions. So there's a lot of research and development that went and still going into creating a good hash function that's at the same time super fast and create less collisions. And in practice, those are the most commonly used ones in real life. Now again, the big guys are the one behind it. The most commonly used one in the real databases is the Facebook XX hash and the Google Farm hash. Those are very fast hash functions. You give them any value, whether it's string, integer, whatever value, and basically they will convert it for you to a number. And they have implementation in various languages, in Python, in C++, and so on. Many databases, they just take them and use them, use those hash functions to implement the hash index. So to implement a hash index, you need a hash function, and those are the practical ones. And I provided here a link, for example, in this one. If you go to Facebook, this XS hash, which is created by Facebook, these are the databases using this hash function. Yeah, many databases actually implement this hashing algorithm in their database implementation. Okay. Now, the other thing that faces us when we are dealing with hashing is that some hash functions, they need, such as the modulus that I just showed you, the modulus, the size. You can see this hash function I started with, where the hash function, it takes the key and does modulus n. The problem is this n here is static, and I need to know it a priori to use it in my hash function. So this is called static hashing, which is not very suitable in the case of database, because the data grows sometimes in a non-expected way, or we cannot really put a figure how many records we will have. It's very hard to put the right figure. So what we really wish to have is to really have some kind of dynamic hashing, where I don't need to know the size of my data structure in which I will be storing my hash values or my values. So in database world, there are two major algorithms that enables this dynamic hashing. One is called extendable hashing, and the other one is called linear hashing. Two major algorithms used for dynamic hashing. that do not require you to have a static hash or a static size of your index. The index could grow, similar to the B-tree. The B-tree, when we created the B-tree, we didn't put any initial size. We start with one node and we keep naturally growing by splitting.